Yo, what's up, guys? Welcome back. Episode 94. Yeah, gonna be doing a few problems today. Let me fix this. Oh my god, I'm gonna sneeze. Okay. I don't need to sneeze. But okay, let's check out Pokemon 94. Pokemon 94. We got a Gengar. Definitely a classic. Probably one of my favorite Pokemons out there. So let's take a look at the sound today.
Gengar, Gengar, Gengar,
Gengar. Gengar. Gengar.
Gengar, Gengar, Gengar,
Gengar.
Gengar, Gengar.
Gengar. There you go. That's our sound. But yeah, we're gonna continue with our doing each one. I believe yesterday we did a graph general. But what I think we're gonna do is we're gonna do course schedule. I know we did course schedule recently because I specifically remember it, but I just kind of want to get that DFS, BFS kind of implementation kind of in my head. Make sure I have that, intuition that I can solve those. We'll probably do one of these BFS ones. Check out a tree, do a backtracking problem maybe, and then, keep going. Then we'll probably call it. So, we forgot to check our problem of the day. Let's check it out. Oh, that's one from yesterday. Yeah. What is this? Redeem. No, I don't want to travel back in time, dude. It's alright. But yeah. Let's jump straight into it. Okay. Let's take a look at course schedule. I believe we should have multiple submissions here. No, it looks like we just have DFS. Okay. There are a total of num courses you have to take labeled from 0 to num courses -1. When did we submit this? April 3rd. About 10 days ago. Given an array prerequisites where prerequisites I indicates you must take course B1 first if you want to take course A1. So we have two courses. To take course 0, you need to take course 1. Or is the other way around? To take course 1, you should have finished course 0, so it is possible. That's what I don't like about this one. To take course 1, you should finish course 0, and to take course 0, you should have finished course 1, so it is impossible. Okay. Okay. Let's try and make our adjacency list here. Def adjacency list, and we can pass in our prerequisites. All right. Create a graph here. Graph is equal to this. For let's just call it edge and prerequisites. We want to do, well, AB is equal to edge. We could do it a different way around too. We could do, well, for the first one would be, we could do for source and prereq in requisites. Okay. In prerequisites, we could do well. We import a default dick. Bro. Okay. How do we initialize it? Prereq in prerequisites. Oh, let me fix my hat. Jeez. So as prereq and prerequisites, we can do, well, we could just do, well, if we need to take course 1, you should have finished course 0. So to take course graph source dot append prereq. Num courses graph I is equal to this. I believe that's what we need. We want to return our graph. Right. Come through here, then call it. Right. So we would do adjacency list graph. Sorry, prerequisites. What we can do, graph is, and then we can do okay. We want to print our graph, right? So print graph. I in range num courses. Okay. Believe that should do the adjacency list. I'm going to make sure that this is a correct implementation. But I believe this is good. Okay. Right, yeah, we don't need this crap. So that should work. I mean, it's same thing, but I was just overriding it, but I guess it's just a little bit of a waste of code, redundant code or whatever. Okay, so pretty much we're looking for cycles in this graph, right? That's the main goal. Def, DFS, passing our graph. We do, well, def, DFS. We pass in our, what do we want? Probably our graph, our visited. No, we probably want our current node. Probably some sort of visited array too, right? We can define our visited array as a new set. Obviously, we just want to call our thing graph. We want to pass in our node, current node, which probably be 0. We can do high and node, right? Because we probably do, well, for I in range num courses. Okay, right, so here we'd be passing in our I, right? We'd enter our DFS function, we check, well, okay. We need a recursive function here, so I guess, well, if I not in, I guess we have to do, well, visited.add I node, right? We check, well, if node not in graph, then for neighbor in graph node, if neighbor not in visited, right, then we want to visited.add neighbor. No, we don't need to do that because we're doing it there when we visit it, right? So we can do, okay, well, graph.append graph node dot, wait, for neighbor in graph. No, we call the DFS function. We don't do this. We would call DFS graph neighbor visited, right? We also want to add it. No, we were doing it there, right? So if we get through So what should this return? It should return true. This should return false. Like we need to check that there too. If it's not in visitor, then we run the DFS, right? Then we check, well, for neighbor and graph. Neighbor not in visited. So if DFS neighbor is equal to false, then we just return false again, right? So how will we know if it's false? Well, if we see a cycle, right? So if node in visited, then we would just return false, right? Then we return it back here and we check, okay, well this is false. That means we completely would just return false, right? If we get through this, then we'd probably just want to return true, right? But there's like some, when we process the node, we process the node here. Whoops, this is meant to be visited. My bad. We would just return false. Otherwise, we'd return true. We check, okay, if node in path, neighbor and graph node, if not DFS neighbor, return false. Don't check if it's in visited. So I guess maybe we're not checking that it's a cycle. Really? if node in path, return false. Path.add node. We keep going through. Path.remove node. Visitor.add node. We build the adjacency list. We create our graph. Visit is equal to set, path is equal to set. For I in range num calls, go through each num and we check, well, if not DFSI, because DFSI, if the DFS function returns false, then obviously we know that it's false, right? We only need one false. So we create okay, so we go through, we check this current node, right? And we go, well, path.add node, right? We go through its neighbors, okay? If the DFS function returns false, so we call DFS on the neighbor, right? This needs to be fixed. This would go to neighbor, right? So if DFS neighbor is equal to false, we would return false, right? So we call DFS neighbor if there's a neighbor. In our case, we would call 0, right? We jump back into here and we check, well, if node is in the path, well, it's not. If node isn't visited, well, it's not. We would add 0, right, to our path. So we have 1, 0, right? We go through its neighbors and we check, well, okay, 0 doesn't have any neighbors. So we would skip this. We would do path.remove node, right? So we'd remove 0. And we do visitor.add 0. We'd come back. We'd return true. We'd jump back. We'd be back at 1 and we go for the next neighbor. Then we don't do that. Then we remove our 1, visited 1, and we'd return true. So that means our function would return true. Everything would return true. If we go to this example here, we have, okay, we start at I, right? So we'd start at 0, right? Pass it in here. Not a path, we wouldn't do any of this. We'd add 0 to our path. We go through its neighbors, right? We see 1 as a neighbor. We call the DFS function on it. Okay, we come in here. Okay, well, none of this stuff matters here. We'd add 1, right? And then we go into its neighbors, right? So for neighboring graph node, if DFS neighbor is equal to false, we call DFS neighbor back on 0 again. And we see, well, that the node's in the path, right? Then we'd return false. We return false here. And then we go back to our 0, right? Go to all the other neighbors, right? Call the DFS function that doesn't have any other neighbors, so then we'd remove I believe take course 1. Okay. I think I understand. I believe this should run now. Yeah. Good. Okay. Gotta check out a different problem. My back though. Oh, dude. That stretch. Okay. I want to check one of these BFS problems, but I'm gonna quickly go shave really quick, and I will be back in a second. What is up, guys? I'm back. Sorry, took a little bit longer than I thought. Yeah. So we're back. Gonna do some more. So, yeah, I think we said we're gonna do snakes and ladders. So let's take a look at this problem. It's a BFS problem. Let's take a look. Given n times n matrix board with cells labeled from 1 to n squared in a Boostropheden style. Aside from the left board, i.e. board n minus 1, 0. N minus 1, 0. Right. This is a... Okay. Choose a square next with the label range curve plus 1 min. This choice simulates the result of a standard 6-sided die roll, i.e. there are always a most success nation regardless of the size of the board. If next has a snake or a ladder, you must move to the destination of that snake or ladder, otherwise you move to next. The game ends when you reach n squared. A board square row in column C has a snake or ladder if board RC does not equal -1. Has a snake or ladder if... Note that you can only take a snake or ladder at most once per dice roll. If the destination to a snake or ladder is the start of another snake or ladder, you do not follow subsequent snake or ladder. Yeah, this is a little confusing. This is the board. Okay. At row 5, column 0. Column 0. 0, 1, 2, 3, 4, 5, row 1, right? To move to square 2, and you must take the ladder to square 15. Okay. You decide to move to square 14. You must take the ladder to square 35. You decide to move to square 36, ending the game. Okay. What is butt pushing in style? I don't know what the hell this is. Okay, so pretty much what we're doing is I think... Okay. Rows is equal to length. Board. Cols is equal to length. Board. 0. Oh, whoops. Let's print out rows. And print out columns. Okay, 0, 0, 0. -1. -1, 15. Right. So how would we get to the next one? This one's all -1s. Then we go to minus. So how does 15? Oh, okay. Okay, so if we land on this one, then we go to 15, I think. If we land on this one, then we go to 35. Which is the ladder up here, I believe. Right? If we land on this one, then we go to 13. Okay. Okay. For row and rows, for coal and coals. Board DQ. Okay. How does this work? Okay, we need to. I believe we just have to roll, right? So we roll. I believe we have to like destroy simulates the result. Choose a destination square next with a label in the range curve +1, min curve +6, and squared. We go from curve +1 to curve +6. So I believe we have to make some like simulation to roll, right? Definitely a confusing problem. Many times in a board representing a game of snakes and ladders, the board is numbered fucked on left to right, right to left, alternation starting from cell 1. If you land on a square that has a ladder or snake, board IJ Highest 1, you must move to that destination immediately. Okay, flatten the board. How the hell do you do this? Is there stakes and ladders deco? Oh, you did do one. Okay.
Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve the problem snakes and ladders, and this is a pretty challenging problem, especially for a medium. It's got some good fundamentals to it, but there's also some uniqueness to this problem that you can't really get in most problems. So we're given an n by n matrix. That means it's a square matrix, just like this one we see over here. It's 6 by 6. Each cell is going to be labeled from 1 to n squared. N squared is going to be the number of cells, of course. And the first one is going to be at the bottom left. That's where the 1 is going to be. 2 is going to be next, and then 3, then 4, then 5, then 6, right? We're going to go to the right in the first row, but then we're going to get the 7 right above that, and then the 7, the next values are going to be towards the left. Then it's going to go to the right. Then it's going to go to the left. So basically it's alternating directions. The order of the values is what I'm talking about, right? 7, 8, 9, it's going to the left, then 13, 14, 15, it's going to the right. So we're going to start at this 1, and we're allowed to roll a dice, and it's a 6-sided dice. So we're either going to roll a value between 1 through 6. Now we don't actually have to generate a random number, so don't worry about that. We're going to try every possibility. If we roll a 1, that means from this starting position, we're going to move 1 spot. That means we're going to move to the 2 spot wherever it happens to be on this grid. If we rolled a 2, we would move 2 spots forward to the 3. If we rolled a 6, we would move 6 spots forward. So we'd move all the way to the 7. Okay, so if this matrix stuff wasn't confusing you enough, there's actually even more complexity. So we have things called snakes. This is a snake and this is a ladder. And this problem is based off a board game that I've never really played, but I think the ladders are supposed to make you advance forward and the snakes are supposed to make you go backwards. But in the context of this problem, in the data structure, the board itself, the 2D matrix, the values of the board are going to be mainly -1s. Right here, you can see the actual values of the board. It's mostly -1s, except for positions that have a ladder on them. So this 15 corresponds to this position. What that means is that in the board there's a 15. That means if we land on this spot, then this ladder is going to take us to position 15. So it's kind of like a shortcut. So if we actually did make this jump to 2, that took us 1 move to do, right? But in the same move, since we landed on a ladder, we're going to advance to this 15 spot. That doesn't take 2 moves for us to do. The advancement is part of the same original move. Similarly, if we landed on this snake, position 17, which corresponds to a value of 13, so if we landed here for whatever reason, then on the same move, we would end up being pushed back to position 13. Now the catch here is, if this isn't confusing enough for you, that we cannot use 2 advancements in the same move, whether it's a snake or it's a ladder. So for example, if there was another ladder over here that took us to position, 28 or something, if we landed here in 1 move, then we would advance to position 15 within the same move, but we can't use a snake or a ladder 2 moves in a row, regardless of what it is. Basically, we're only allowed to use a snake or a ladder once per move. So only after we move are we then allowed to use a single ladder. But then when we get to the second ladder within the same exact move, we're not allowed to use it. right, within the same move. So if we did land on this 15, then let's say we got to our second move, right? Then are we allowed to use this ladder? No, we still can't. We have to roll the dice, and the dice means we have to advance between 1 through 6 positions. Okay, so I would say probably the hardest thing about this problem is just trying to understand it. And let's actually read the rest of this question to make sure that we do. The main thing we're actually going to be returning is the minimum number of moves required to reach the last square, right? So in this case, 36. Okay, so now that we understand the question, let's actually try to start with a solution. And as always, let's start with a brute force approach. So initially, we're always going to start at the square 1. And our goal is to get to the n square position in the minimum number of moves. First thing, let's try every possibility, right? Well, we know we can move between 6 positions, right? So from 1, we can move to 2, 3, 4, 5, 6, 7. But we know that 2 actually has a ladder on it. How are we going to know that? Because we're going to check the position here, right? In the board, we're going to convert 2 into some coordinate, right? Some row, column, pair, and we're going to use these to index the board and get the value at this position. And what value is that going to be? Well, if it was -1, then that would mean there's no advancement, right? Basically, basically 3, 4, 5, 6, 7, they all have -1s in the board. You can kind of see it over here, even though it's not super clean, but they're going to have -1s. But this 2 position is going to have a 15. That means there's an advancement, right? 15. So basically that means instead of when we land on position 2, we're not really at 2, we're at 15 because we just used the advancement. But now the question is, how are we going to convert a position like 2 or 9 or, whatever 28 to a row column pair? How are we going to do that?
Flatten
Well,
it.
let's just assume for now that we have a helper function to do that. Because this problem is complicated enough, we need to modularize this code. So let's not get bogged down on the details. We'll work on that implementation last. For now, let's assume we have one that's working. So in our decision tree, this 2 will really be a 15. And now let's continue this brute force. But as you can tell, this decision tree is going to get really huge, right? Because each time, each node is going to have 6 children. So I am going to take some, shortcuts, but I'm going to explain the intuition behind it. So now let's do 3, right? Assuming we were doing the decisions for 3, we would do, 4, 5, 6, 7, etc. But are you noticing anything? 4, 5, 6, hey, we already have those in our decision tree. Why would we want to revisit them again? And remember, we're looking for the shortest path. Why would we care to reach 4, 5, and 6 after taking 2 steps, even though we reached 4, 5, and 6 by just taking 1 step? So there's no need to revisit any of the positions. So how are we going to prevent that? Let's have a hash set and let's call it visit, and let's make sure that we never revisit the same position twice. Okay, so that's one thing that we learned, and I'm not really going to draw out the children for these because from this picture, picture and the explanation below, you can tell that the shortest path is going to be from 1 to 2, which actually landed us at 15, and then from 15 to 17, which actually lands us at 13, and then from 13 to 14, which actually lands us at 35. So you can kind of see the circuit that I'm drawing here, and then from 35, we'll take one jump and get to 36. So you can tell, okay, 1 move, 2 moves, 3 moves, and 4 moves. So that's the path. But from this decision tree, how can we actually create the algorithm for that? Well, the visit set that we talked about is very important because that will basically limit us for the time complexity being the overall size of the board, which is going to be n squared. But to actually implement this algorithm, it might be possible to do this with a DFS. I'm actually not 100% sure, but I think it would work as long as you aren't visiting the same position twice. But the more natural way to do it is breadth first search, and that's usually the algorithm you want to do for shortest paths. And let me kind of show you the intuition of why, because as we're drawing this decision tree, these are the positions we can reach after 1 move. As we continue it, suppose from 15, we can land at 16, 17, and actually 17 will land us at 13, as I mentioned, so we can't actually land at 17, but we can also do 18, 19, 20, and lastly 21. And so these are the positions we can reach in 2 moves, right? And the next layer of our graph is going to be all the positions we can reach in 3 moves, etc., until we finally reach the last one. And so we could possibly create this graph with a DFS approach, but it doesn't really make a lot of sense. It would be better to do this with BFS and then continue that until we finally get 36 to show up in one of these layers. And it's possible that I think we might not even have a path to get to that. I don't know what that would even look like. Maybe there's like an infinite number of snakes that just keep taking you backwards. And if that is the case, for the number of moves, we're going to return -1, basically indicating that there's no solution. But if there is a way, in this case there is, from 15 to 13 and then 13 to 14, which will actually lead us to 35, and then from 35 to 36, we basically are returning the number of moves. In other words, the height of this decision tree, which in our case is going to be 4, and that's the same that they had as well. And you can read through this explanation if it makes more sense to you, but I think that's enough for us to start writing the code. But one thing I will revisit is how can we take a value like 9 and then convert it to its row column coordinates. First things first, let's get the length of this board because we know that's going to come in handy, and we know that the board is never going to be empty. And let's just define a helper function for now, but I'm actually not going to actually write it out. So it's going to be int to position. So basically it's going to take some number, like some square, whatever the label happens to be. In our case, it was 1 through 36, and it's going to return some row column coordinates. But for now, we're not going to implement this. Let's just assume that it works. And then we're actually going to get started on our breadth first search. So we're going to create a deck, a queue, which is usually used for BFS. And we're actually going to have a pair of values. Since we're looking for the shortest path, one value is going to be what square are we at? Like that's kind of the position in our case. Usually with graph algorithms, you have a coordinate, but like a row column pair. But in this case, we're just going to use the square itself. And the second value is going to be how many moves did it take us to get to this square. So initially we're just going to append to our queue 1 because we know that's the starting position, and the number of moves it took us to get there is of course going to be 0. And the second data structure we talked about was a set, a hash set in this case, which is going to just take care of how many, which positions have already been visited. And then we're going to get started on the standard algorithm, which is BFS, but there's going to be some adjustments we're going to have to make because of course we're going to need to convert the square into the actual coordinates as well. But as usual with the BFS, we're always going to be popping from the left and then adding to the right side. And popping it is going to give us a pair of values, the square and the number of moves it took us to get here. And then from this square, we're going to do the portion where we roll a dice. The value of the dice could be 1 through 6. So in Python, it's going to be a little bit weird. Of course, it's going to be starting at 1, but the second value is non-inclusive, so we're going to put a 7. What this is really doing is I is going through 1 through 6. And then using that I value, we can add it to the square that we had, which will give us the next square value. So pretty simple so far, square plus I. But now we're actually going to want the coordinates of the next square. And you're going to see why we're getting the coordinates in a moment. So let's pass the next square in. So that will give us the coordinates. But what's the point of having the coordinates? Well, if you remember, the coordinates are used to get what's the value in the board at that position. Because remember, if the value is -1, then we don't really care about it. But if it's not -1, that's important because that means we found a shortcut or maybe a snake that's going to take us backwards. Either way, we want to know what, if it's not -1, what is the value of that, because that's going to be the next square. Within the same move, we made one jump and now we're about to make a second jump because there's either a snake or a ladder. So we're going to reassign the next square to whatever that value in the board happens to be. Maybe it took us forward, maybe it took us backwards. And next thing, before we even add this next square to the queue, we're going to check maybe it's the solution, right? Maybe this next square is equal to the length squared. And if that is the case, that means we found our solution. And we're going to return the number of moves it took us to get here. Remember, moves was the number of moves it took us to get to this square, and then we made one more move to get to the next square, so we're going to return moves plus 1. Okay, but if we didn't find the solution, then we're going to add it to our queue, but we don't want to ever revisit the same position twice, so let's make sure that this next square is not in our visit hash set, and if it's not, then we're going to add it to the visit hash set to make sure we never revisit it twice, and we're also going to append it to the queue, but we know that our queue actually has a pair of values, which is going to be the square value itself and also the number of moves it took us to get here, which is moves plus 1. Okay, so assuming that this works, we will return the number of moves, but let's say it doesn't work, then once we exit the loop, they want us to return a default value of -1. I don't even know if there's an actual test case that covers this. There probably is though. Okay, so we've actually pretty much done the algorithm except for the most annoying part, which is going to be converting a square to the actual coordinates. And to do that, I'm actually going to go back to the drawing. So the way that this board is actually given to us, this is the 0th row, this is the 1 row, this is the 2 row, this is the 3 row, 4, and the actual columns themselves are actually straightforward, 0, 1, 2, 3, 4, 5. But my problem with this is we're starting at the 5th row. That's a little bit unintuitive. It's basically going to overcomplicate the calculation in my opinion. So wouldn't it be a little bit easier if the way the rows were labeled as 0, 1, 2, 3, 4, 5, like we're starting at the 0th row. That makes more sense to me. And we're trying to get to the last row. Now you can still do it the other way if you want to. It's not a big deal, but I'm just going to do it this way. I think it's a little bit more simple. So the way we're going to do it this way is just basically just taking this board that we're given and reversing it. What that's going to do is it's going to reverse each row in the board so that this is going to be the 0th row. Okay, once we have that, how are we going to be able to take one of these values and convert it to this row and this column? Well, another annoying thing about this is the values start at 1. In programming, we usually start at 0, and that makes the calculations work out a little bit better. Whenever we take a value like 9 into our function and then convert it to the row column pair, we're actually going to take this and subtract 1 from it, just to make sure that we're actually starting at 0. So let's say we took a value like 9 and then we subtract 1 from it. Now we have 8. How can we convert 8 into the row column pair? To get the row is actually really easy. We just take this value and divide it by the length of the board, which in this case is 6. So if we take 8 and divide it by n in this case is 6, we're going to get 1 because we're going to round down, right? And as you can see, that does work out in this case. Now, what if we had 12 as the input? Well, we're going to take 12 minus 1, which is 11, divided by 6, that's also going to be 1. So it does work. Okay, but how are we going to calculate the column? That's actually going to be really hard, and the reason is because it's alternating. If it wasn't alternating, it would actually be really trivial, because for the even rows, like 1 through 6, we can just take the value 4, and we're always going to subtract 1 from it, so 4 minus 1 is going to be 3, and then to calculate the column index is just going to be that value, which is now 3, modded by 6, and in this case it's going to be 3. And that makes sense, right? Because this is index 0, this is index 1, this is index 2, this is index 3, right? So that makes a lot of sense. And you know, if we jump to the next even row, it also makes a lot of sense, because this row is just going to be 4 plus 12, and then that 12 is just going to get canceled out by this mod operation, and then 16 minus 1 is going to be 15, modded by 6 is going to be 3 again. So that makes sense, right? All of these are going to be 3, but the annoying part is, you know, when we make 2 jumps, we're adding 12, that makes sense, but when we make 1 jump, we don't really know what we're adding because this is alternating. Remember, we're going this way and then we're going that way. So how do we correct that? Well, we're going to check if the row is an odd index. We're going to do some special calculation. We're still going to say, okay, with our general calculation, where we just take that value, minus 1, and then mod it by 6, we're going to end up saying 7 is actually over here, but it's not over there. We actually want to put it in the correct spot, and when we try doing 12, we're going to find that the column for 12 is going to be over here, but it's not. We actually want it to be over here. So how are we going to do that? Well, as you can tell, we're basically flipping these positions, right? This is going to be flipped with this, and then this is going to be flipped with this, and it's going to go both ways, right? So the way to kind of do that, let's just draw it out, 0, 1, 2. So to actually do that, what we're going to do is we're going to take the length, let's call that n. N is just the dimension, minus 1, because n is going to be 6, but the max is really 5. So that's where the minus 1 comes from. And then minus whatever that column that we end up calculating. So in this case, if we got a 5, if we calculated a 5, we'd say 6 minus 1 minus 5, which is going to put it to be 0, meaning this is going to be moved over there. If we calculated a 0, we'd say, okay, 6 minus 1 minus 0, that's going to be 5, so that's going to take this 0 and then put it at this position. So that's really the intuition behind it. Maybe I spent a little bit too much time on this part, but now let's just code it up. Okay, so as I mentioned, first we're going to calculate the row, and that's going to be square, and we're always going to subtract 1 from the square, and then we're going to divide it by whatever the length of the board was, which we calculated up here. And this is integer division in Python. That just means it's going to round it down, which is exactly what we want to do. Okay, and then we're going to calculate the column. We're going to calculate it in the naive way. First, make sure to subtract 1 from the square, and then just mod it by the length. That will work for us as long as the row is not odd. If the row is odd, and we can figure that out like this. So in this case, if the row is odd, we need to reassign this column, and we're going to do it exactly how I said. We're going to set a column equal to length minus 1 minus itself. Okay, so that's almost the whole code, but one thing I almost forgot is we were actually going to reverse the board, because remember, we want the 0th row to actually start at the bottom of the board. So just by reversing it, we can do that. And that's why this function is pretty simple. If we didn't do it that way, it would just be a little bit more like, we'd have more calculations that look like this one. And I don't really like explaining how this works. Now let's run it to make sure that it works. And as you can see on the left, yes, it does, and it's pretty efficient. The overall time complexity of this is going to be in the worst case n squared, because we could end up visiting every position in the board. And the memory complexity is also going to be that, because of how the breadth first search is working. We could have, every value be in our queue. So I really hope that this was helpful. If it was, please like and subscribe. It really supports the channel a lot. Consider checking out my Patreon if you'd like to further support the channel, and hopefully I'll see you pretty
Okay, let's take a shot at this problem, right? Okay, let's calculate the length of the board, right? The length is equal to the length of the board, right? We can create our Sorry, what do we want to call it? Get board index, right? We want to pass in our actual what do we call this on a board, man? Jeez. Let's just call it like index for now. I don't know. Right? And this returns a row column, right? So row column, but we need it like this, right? Let's do our BFS function. That's the most important thing when we think about this problem. We have our queue, so we want to do, okay, our Q is equal to DQ. I'm going to pass in our 1 and our 0, right? Because our 1 and our 0, our 1 is considered as, well, I know the second one's our level, right? The first one would have to be, I guess, like current position, right? Square. Yeah, current position. I guess the same thing, but whatever. Okay. We have a while queue. We also want to have a visited set, right? Visited is equal to set. While queue. We want to pop, right? So we pop, well, our square and our level is equal to q dot pop left, right? Then we want to loop through. We pop. We want to check, well, it's the first thing we want to look at. We want to check, well, if square does not equal -1. Right, it's because we're going to start here. We're going to check, well, is this -1, right? If it doesn't equal -1, then we want to do many different things, right? So, okay. Never mind, I forgot. We have to do our for loop, right? For I in range 1 through 7, okay? We want to get position is equal to get board index. We pass in our square, our current square plus I, right? What does he call it? He calls it next square, right? Once we get our next square, then what do we want to do? We want to check if next square does not equal 1. If next square does not equal -1, I guess we have to call that method. I guess it returns RC, so it would be RC like this. Okay. If board RC does not equal -1, then what would we want to do? We would probably want to If it doesn't equal -1, we'd want to get that value, right? Because if it doesn't equal -1, it's taking us to the next value. So how do we guess we'd probably want to check, well, if an x square is equal to the last element over here, then we'd want to return our what do we want to return? Return our level y level plus y. Oh yes, because technically, yeah, we're doing the next value here, right? If not, I guess we just want to append our next square, right? So we would do, well, we want it, if next square not in visited, then this is when we want to append. We do, well, q.append q.append next square level plus 1. I want to add to our visitor too. Okay, now it comes to getting our board index, right? So I guess we forgot our -1. Get our board index, we need to reverse our row. This is what I don't really understand. Board is equal to board.reverse. Right? Is that what you do? Board.reverse. I want to make it equal to something. We just want to do board.reverse. And here, how do we do this? R is equal to the square -1 divided by the length. C is equal to the square -1 modulus the length. And then we want to check, well, if R modulus 2 does not equal 0, so we know that it's odd, then C is equal to length -1 minus C. We would just return the row column. Can't unpack iterable object. I think we need more parentheses here. Cannot access like a variable next square is associated with a value. I'm not sure. I'm not sure why I'm getting this. Cannot access local variable next square where it's not associated with a value. Ah, okay, I understand. It's only associated inside the box. So that's why we need a next square here. Next square is equal to square plus I. Then next square. Why am I getting the wrong answer here? Okay. My bad. Okay. That was a tough problem, man. I understand the BFS part, but I definitely need to have a relook at this board index part. Definitely confusing. Got a lot more working to do. Definitely. Yeah, we're gonna call there on that problem. I will be back again. I'm gonna go get some lunch with some friends. And then we're gonna continue doing the problems. So we'll see you guys soon. Yo, what's up, guys? We're back. Let me just fix my mic here. Oh, that's not working. Okay, I think we're good. Welcome back. Been about 4 hours. Had some lunch, hung out with some friends. We got Indian food, and I ate way too much, so I need to take a nap too. So yeah, we're about 4 hours later, and yeah, let's take a look. So I believe the next thing we were talking about is we were going to implement whatever a tree is, and I'm a little confused what it is. It's a tree-like data structure used to efficiently store and retrieve strings. It's particularly useful for applications involving string searching, auto completion, and spell checking. Each node in the tree represents a character. Maybe we can get a little video going here. Tree in 5 minutes.
How's it going, you guys? So today we are going to implement the try data structure. Being able to implement this data structure is very important. On Leetcode, this question has been asked at Amazon, Facebook, Google, and Microsoft. So before I get into the video, definitely like and subscribe. It really helps out the channel. And don't forget to check out my Patreon if you want to support me further. So this video is more focused on the implementation of a try rather than explaining exactly where a try is used. If you want a more in-depth explanation as to what a try data structure is, I have another video explaining it, and the link will be in the description. But to summarize, a try is a tree data structure where the nodes store letters inside of the alphabet, and we can connect these nodes together to just store words inside of it. So I'm going to walk through a full example as to what we have to do to implement this try data structure. we need to implement the following functions: insert, search, and starts with. Our insert function will just insert a word inside of our try. The search function will determine if a word is present inside of the try. And lastly, the starts with function will determine if a certain prefix is inside of it. If we look at the notes that are provided in the problem description, you can see that it says you may assume that all inputs consist of lowercase letters A to Z. Additionally, all inputs are guaranteed to be non-empty strings. So the first note is very important. We don't have to worry about any other letters other than just lowercase letters. So each node inside of our try will have the possibility to have up to 26 children, where each child is an individual lowercase letters, A, B, C, D, all the way up to Z. So let's say we want to insert the words cats and cape inside of our try. Initially, we're just going to have a dummy node as our root. In order to insert the word cats, we would create a node for each individual character in that word. So we would have a new node for C, a new node for A, a new node for T, and a new node for S. And then all of these nodes would be connected together. So A would be a child of C, T would be a child of A, and S would be a child of T. As for inserting cape, we can see that our first character is a C, and we've already created a node C. So that means we move to character A. Once again, we've already created that node. Then we move to characters P and E, and we have to create nodes for both of those characters. Node P will be connected to node A, and E will be connected to P. Now that we've inserted both words, we need to determine at which point we've actually created the words. So for example, if we were going down this tree data structure, if we go to character A, CA is not a word. However, when we go down to character S, that would be a word at that point because we went from CATS. So all we need to do is label which nodes are words. So that would be character S and character E. An easy way to think about this is the last character in whatever word that we're inserting will be the node that is marked as a word. Doing this step is very important because this is how go down to character S, that would be a word at that point because we went from CATS. So all we need to do is label which nodes are words. So that would be character S and character E. An easy way to think about this is the last character in whatever word that we're inserting will be the node that is marked as a word. Doing this step is very important because this is how we are going to implement our search function. So for example, let's say we wanted to search for the word cat. We would find C, find A, find T, but node T is not marked as a word. So we would actually return false. But then if we said, let's search for cats, we would go from CATS, and since S is marked as a word, that means we would return true. However, the logic for the function starts with is a little bit different. For example, let's say we wanted to check if any word inside of our try starts with cap. We would go from C to A to P, and since all of those nodes in that exact path were created, that means we would return true from our function. Okay, so let's implement the code. We have to implement this try class. The first thing we're going to want to do is create a node class in order to store all of the individual letters. So we can come down here and say class node, and inside of it we're going to have a couple different attributes. We're going to have obviously the character, we can just call it C. We're also going to have a boolean which says if the node is a word or not at that point. And then finally, we're going to need to store all 26 children potentially. So to do this, we can just use an array of size 26. So we can say node, and we can call them children. And then inside of our constructor, we're going to be passing in our character. So we can say this.c equals c. Is word is just going to be initialized to false. And then finally, we're going to initialize our children array. and this will be of size 26. The reason why it has to be 26 is because remember, we're only dealing with lowercase letters. So each index from 0 to 25 will be responsible for storing one character. So index 0 will map to character A, index 1 will map to character B, index 2 to character C, and so on. So this children attribute is the main reason why it is considered a tree data structure, because every single node is going to be pointing to up to 26 different other nodes. So now that we have this class implemented, we can start implementing the class try. So the first thing we want to do is we need to create some sort of dummy node. So we can say node root, and then inside of our constructor, we can say root equals new node, and we can initialize the node, our root, to have really any character because we're not going to be using this root node. So what I like to do is just do /0, and this pretty much just means that it's an empty character. Now we can start implementing our insert function. The first thing we want to do is we want to keep track of a current node that we're moving through our tree data structure with. So we're going to create another node, and we can call it cur, and this will always start at the root, at the very top of our tree. And now we need to loop over all of our characters. So we could say int I is less than word dot length. And then inside of here, we need to extract the character. So we could say word char at I. So this is where it kind of gets interesting. We need to check if current already has a node created at character C. So this will make more sense once we write it out in code. So we can say if cur.children of C minus character A, if that's equal to null, then we need to create the node. So we'll say cur.children C minus A equals new node of character C. So the reason why we're doing C minus A is because character A has a certain decimal value. So whatever character that we're getting, we can always subtract it by character A, and that will be an index between 0 and 25. Technically, we could have implemented this using like a map data structure, but this is much easier to write. You just have to understand why you have to subtract it by character A. So if the node at that index is null, then we're just creating it. And this is kind of where the inserting magic happens. We're creating the new node with that character C at that index. Once we come out of this if statement, we know that that node has already been created. So we can say cur equals cur.children at C minus character A. So this step is actually moving down the chain inside of our tree. And once we come out of this for loop, we're going to mark whatever our current node is. We're going to say cur.isWord, and that is going to be equal to true. The reason why we do this is because remember, the very last character in whatever word that we're inserting, we always need to mark that node as the word is true. So now we can move on to implementing search and starts with. As you can probably imagine, both of these functions are very, very similar. So we can actually just have another helper function that both of these functions call. So what we want to do in this helper function is we're going to return a node, and we're going to say get node, and we're going to pass in the word that we are looking for. So how's it going, you guys?
Oh my gosh,
today
dude.
we are going to over the word that we passed in. So we say word.length I++. Just like before, we're going to extract the character, word char at I. And now we need to check if the node at character C is even created. If the node at character C is null, then we just return null from this helper function because there is no node that has that path of characters. So we can say if cur.children C minus character A, if it's equal to null, then just return null. We can't move forward. Once we come out of this if statement, just like before, we need to move our cur. So we'll say cur.children C minus character A. And then when we come out of the for loop, all we need to do is return cur, because cur is the very last character inside of that word. And now we can use this helper function to implement our search. So the first thing we want to do is say node is equal to get node at the word. So we're searching if that specific word is inside of our try. So pretty much all we need to do is check if node is word is equal to true. So we can go down here, we'll say return if node is not equal to null, because remember, get node has the potential to return null. So we have to do that check before. And node is word. And now for starts with, it's actually even simpler. We just need to make sure that the node that we're looking for is not equal to null. So we can say return get node at the prefix not equal to null. If the node that we return is not equal to null, that must mean that the prefix was inside of our try. All right, so that is it for a try data structure. Let's just make sure that this solution works. So our time complexity for insert, search, and starts with will all be O of M, where M is the number of characters that
I think we don't need to implement that. I don't think we need to implement it. I'm just going to double check. Java implementation. C++. I thought. Yeah, we do the starts with the search, the insert. Maybe we do. Self-taught children. Right from A to Z. No, I'm not really 100% sure. We want to create our tree node data structure. Here, so. like self dot root is equal to, how do we do it? Node like this, I think. Maybe that worked, I don't know. Oh shit. Whoops, meant to be try node. Man, what the hell? Okay, our insert. How did we do our insert?
Track of a current node that we're moving through our tree data structure with. So we're going to create another node.
So tree node. Sorry, no. Self.cur is equal to tree node.
And we can call it cur. And this will always start at the root, at the very top of our tree.
I didn't root like that. Oh, maybe we can just do cur is equal to self.root, because wouldn't that work as well? Cur is equal to self.root.
And now we need to loop over all of our characters. So we can
Loop over all of our characters.
say int I is less than word dot length. And then inside of here, we need to extract the character. So we could say word
char is equal to
char at I. So this is where it kind of gets interesting. We need to check if current already has a node created at character C. So this will make more sense once we write it out in code. So we can say if cur.children of C minus character A, if that's equal to null, then we need to create the node. So we'll say cur.children C minus A equals new node of character C. So the reason why we're doing C minus A is because character A has a certain decimal value. So whatever character that we're getting, we can always subtract it by character A, and that will be
they say here if char not in children, then we can create a new node. So node dot children char is equal to a new tree node. Cur here. Cur is equal to node dot children char. And then we get to the end of it and we do, well, is equal to true. The Python solution is much more simple. Like, char not in cur is equal to cur dot this is where we move it to the next value. We loop through. If char not in cur children, we instantly return false. If it is, we move it, right? And we would return cur dot end word. If it starts with cur is equal to self dot root, we loop through the char and prefix, right? We check, well, if char not in prefix, then obviously we would return false. Otherwise, we'd move to our next value. If we get through everything, I believe we would just return true, right? I think. List indices must be integers or slices. List indices must be slices, not. I don't know what's wrong. Why are we getting a type error? Using a list, right, which uses indexes, but you're checking if char not in co.children and trying co.children char, which is only valid if children is a dictionary. For char in Word, if char not in. Okay, we need a map. What a, right, which gives us our map. If char not in co.children, then we'd map it to the index, right? Equal to tree, no. Co is equal. Turn false, we make car is equal. This needs to be indexed now. X is equal to. this is like the maybe 6th or 7th bottle of water I've drank today, bro. It's insane. I've pissed like 5 times now. So what could be different here is we're mapping here, but instead this could be a dictionary, right? So we could have a dictionary holding 26 values. And if that char is linked to there, it could work. But this is the way that he showed us in the video where we map. Interesting problem. Let's learn about a little bit about a heap today. I think we'll call it a day. I just kind of want to have a good idea about these data structures, right? So then we'd be kind of, you know, we'd have a good understanding about everything. I don't even think I've done a heap problem, as you can see here. Let's see if there's like a heap problem, like an easy heap problem. Let's do like an easy heap. Oh shit. Is there an easy difficulty? Okay, sweet. Let's do it by acceptance. Maximum product of 2 elements in an array. Right. I think this would be an easy one to learn. Learn priority queue data structure in 5 minutes. I'm using bro code.
Hey everybody, it's your bro, hope you're doing well, and in this video we're going to discuss priority queues in computer science. So sit back, relax, and enjoy the show. Hey, what's going on everybody? So priority queues. A priority queue is a FIFO data structure, first in, first out. However, a major difference with priority queues is that before we start polling and serving elements, we put them in some sort of order. Higher priority elements are served first, before elements with lower priority. So here's an example. Let's say that we have some student GPAs, and we'll place them all within a queue, and then a priority queue, and take a look at the differences. So let's create a queue. The data type is queue, and we are going to insert some doubles, some GPAs. I'll name this queue equals new. Now queues are actually interfaces and we can't implement them directly, so we need to use a class that utilizes the queue interface. One that I know of is a linked list. Then finish instantiating it. Now to add data to a queue, we use the offer method. Queue.offer, and then pass in a GPA. Let's make sure that these are not in order. How about a 3.0? Then the next student has a, let's say 2.5. Then a 4.0, 1.5, and 2.0. Okay, now let's display the elements of our queue. One easy way in which we can do that is to use a while loop. And this is our condition. We'll continue this while not logical operator queue dot is empty method. While our queue is not empty, poll each element and display it. So within a print line statement, let's use q.pull to display and remove each element, beginning with the first one and then working our way to the end. So this will display the elements within my queue. So these are in first come, first serve order. Whatever element we were offered first, we are serving that element first. If an element was added last, well then it's served last. So that's a standard queue. Now with a priority queue, we're going to arrange them in some sort of order before we actually pull these elements. So let's change our linked list to a priority queue. And run this again, and let's take a look at the differences. Okay, these are all in order now. So if we're working with numbers like doubles, these are arranged in ascending order, beginning with the smallest element. Let's pretend that these are grade point averages, GPAs. Why might we want to put these in order? Let's say whatever student performed the worst gets 2 hours of free tutoring, whichever student performed second worst gets 1 hour of free tutoring, and third gets half an hour of free tutoring. Now if you need these in descending order, well there's one change that we're going to make. Within the constructor we can pass in a comparator, but that's a little advanced for us and we haven't discussed that yet. So there is a default comparator that we can use found within collections. Collections dot reverse order method. So these elements will be in reverse order then. In this example, let's say that whichever student has the best GPA will receive, I don't know, a gold medal, like the Olympics. And the second best student will receive a silver medal, then a bronze medal. And then every student after that, I guess, will receive nothing. But that's okay though, they got some free tutoring in the last example. Okay, now let's change the data type. Let's say that these are now strings. And let's put these in standard order. So let's change these to strings. Maybe this student has a B. This one has a C. And well then, these elements will be in alphabetical order. So if we need these in reverse alphabetical order, again, we can pass in a comparator. And then one that we can use is from collections. Collections dot reverse order. And these elements within our priority queue are now within reverse alphabetical order. So yeah, that's a priority queue. Think of it like a queue. However, we first sort these elements based on a...
Okay. Let's see if we can do this problem out. So we're given an array integer of numbers. Choose two different entities I and j of that array. Return the maximum value. Okay. So in this case here, the maximum value would be... You just use I and j. Next from 0, you would get the maximum value that is nums I 1, 12. So we would do 3 times 4 is 12. Okay. So how do we create a priority queue? How to queue in Python. Import heap queue. Import heap queue. Okay. Heap queue dot heap push. Let's do okay. PQ. Let's take this. Let's do for I in nums. Heap queue dot heap push. We do fucking I or something? Print PQ. 2, 3, 5, 4. Okay. But it's in linear time, heapify. Okay, heap.heapify x, transform the list into a heap in place in linear time. Let's see what this does. Oh. What is this, bro? What is a min heap? What is a min heap? Min heap is a type of heap data structure where the parent node is always less than or equal to its children. Oh, okay, that must explain the listing here. Where the parent node is always less than or equal to its children. Noob coder. Convert a regular list into a heap, but you don't need it to be used. You push every element. Heaps in Python, dude. Take a look at this video. Damn, bro, what an intro, bro.
What is going on, guys? Welcome back. In today's video we're going to learn how to use a heap in Python and thus also how to use a priority queue in Python. And the difference between those two terms is basically that a priority queue is just an abstract description of what this data type or data structure does, and a heap is a concrete data structure, so something you can implement. Now today we're not really going to implement the heap from scratch as we have done with the binary tree. We're going to use a library in Python called heap_q. So we can just go ahead and say import heap_q, and this allows us to use the heap in Python. But before we do that, I want to cover some theory here, some basic theory here for those of you who don't know what a priority queue is or what a heap is. Now, a priority queue, as the name already says, is a queue that structures elements or orders elements by priority. So let's say we have,
This is going to be such a refresher,
multi-line
man.
comment here. Let's say we have some tasks. T1 has a priority of 5, and T2 has a priority of 4, and T3 has a priority of 7. And then maybe we can say something like T4 has 9, and T5 has 2, and then T6 has 6, or something like that. So these are the priorities, and we can say now the lower the number, the more important the task is. Now, a priority queue is a data structure that gives us always the element with the highest priority next, or with the best priority. So in this case, the lowest number. So a priority queue would be a data structure that has all these elements, and when I say next or give me the next element, I get this one here. Then I process it, so I take it out of the queue, and when I say next, I get this one here, and when I say next, I get this one here, and so on and so forth. And also, we want to have something that's quite efficient, so we want to have something that when I add a new element here, let's say T7, and I say this has the priority 1 or 3 or whatever, it is structured in a proper way. So when I say next, I get this, and when I say next again, I get this one here. So I want to have something where it's efficient to insert elements and to get them out of there. So basically a priority queue that is also efficient when it comes to the functions that it uses. And this is what a heap allows us to do. Basically, a heap is an implementation of a priority queue, an effective and efficient implementation of a priority queue, and it is a tree data structure. So I'm going to use some drawing tools here in order to basically explain to you what a heap is. And a heap has actually a very basic property. Depending on whether it's a max heap or a min heap, we have a core element or a root element that has a certain value, let's say for example 4. And the rule is now that every element that comes below that, so we have children here, every element that comes below that has to be either less or greater than it. So in a min heap, if we have a min heap, each element here has to be larger than 4. So we have to have, for example, 10 and 5. And then each child of those nodes has again to fulfill this property. So in this case, we can have something like 15. It's not the most beautiful drawing here right now, 15 or 11, for example. Or we can say, okay, 5 has 6 as a child, or also 5 is possible, so equal is also possible. But this is a min heap. So in a min heap, we have the smallest element at the top. This is the basic idea here. This is why it works as a priority queue. So in a min heap, the lower the number, the higher the priority. In this case, we could say, okay, give me the next element. All we need to do here is we need to take this element here, remove it from the heap, and then we have the smallest element, so the element with the highest priority. And then we use something called heapify to basically restructure the tree in a way that it fulfills this property again. So then the 5 would be at the top, and so on and so forth. And with a max heap, it's the opposite. So in a max heap, we have an element here like 10, and each element below it has to be less or equal. So something like 8, or also 10 is fine, and so on. So that's the basic idea of a heap. We're not going to implement the heapify and all these things ourselves. We're going to use heap_q for that. But we're going to create a simple list of values. So we're going to say h is equal to, and now we're going to use, or let's say just data, let's call this data, is going to have a couple of values here, 10, 20, 43, 1, 2, 65, 17, 44, 2 again, maybe 3, 1, whatever. And essentially, this is now just some data. This is not a structured data. This is not sorted. We don't have a priority queue here. Now, you might say for a priority queue, wouldn't it be enough to just sort this list? So wouldn't it be enough to just say, okay, sort or sorted? Like, let's print that sorted data. Wouldn't that be enough? I'm not sure if this is a list. There you go. So wouldn't that be enough actually? And yes, for this if the data stays like that, it would be enough. But the problem is that now if we want to insert a new element, we have to go through the list, and we have linear runtime complexity and so on. So we don't want to have that. We want to have an efficient way of inserting data. And in a heap, we just have to insert it at the end, and then we have to do this heapify operation. And the maximum amount of steps we need is logarithmic. So the runtime complexity in a heap for entering a new element, inserting a new element, is actually logarithmic, which is better than linear. If you want to know more about runtime complexity, take a look at my algorithms and data structures course. It's for free on YouTube, I think 4 hours. There I cover more theory. And essentially we have now this data. And in order to turn this data into a heap, what we do is we say heap, or let's say heap data equals heap q, or actually we don't need to return it. I think we just say heap q heapify data, and then we can print the data, and it's going to be heapified. And essentially you can see now maybe that you don't really see a structure that you understand. So what does it mean? Why do I have 1 1 here and then 17 here and then 2 2 here? It doesn't look very structured. The idea is the following: you have a certain node I, and the first child of I, let me just look this up again in order to not mess this up, but the first child is at the index. So if you're currently at the index I, your first child is at the index 2 times I plus 1, and your second child is at the index 2 times I plus 2, and your parent node is essentially at I minus 1 divided by 2. So this is the rule. This is not too important, so let's just focus on the children. In this case here we have index 0, so the first child of index 0, we can actually use some plotting here. So we have 1 here being the root node, so this here, and then the first child is 2 times 0 plus 1, so this here. So the first child is 1. Then the second child is this here, because we have again 0 plus 2. And then for those, what we have to do is we have to go to 1, and we take 1 times 2, so we have 2 now, plus 1. So this is the first child, this is the second child. Essentially you can just keep going like that. We have 2, 2, then we have here 65, and so on and so forth. You basically just follow the instructions here. Then you have a 3 here and so on. But this is how it works. So we have always the first child at this index and the second child at this index if the current index that you're looking at is this. And this is how the heap is structured now. So this is a priority queue now, because if I want to get the next element, I can just pop the element. So I can just go ahead and say print heap queue dot heap pop, and I can say data. And then I get the element with the highest priority, so with the lowest value, in this case 1. This is a min heap by default. And you can also see that if I do this and I print data afterwards, this is still going to have the proper tree structure. So it's not just taking the first element and then leaving the rest as it was. You can see now that the 2 comes before the 17, even though this was not the case here. So it's also heapified already. It's the same thing as just going ahead, like let me do that here real quick. Let's say we have a copy, and the copy is essentially the data, the list here. Basically, it's heapified already. And what we're going to do now is we're going to heap pop for the data, but we're going to just pop for the copy. So copy.pop 0, so pop the first element. We get the same element, so we can pop the same element, but the problem is that if I now go ahead and say print data and print copy, you're going to see that the data is heapified and the copy is not. So in order to heapify the copy, I would have to call heapify again, whereas heap pop pops and heapifies. So heap q dot heapify copy, then we would get the same result here. Or actually we don't. Why is that? Yeah, because I have to... No, what's the problem here? We heapify, we copy the data, we heap up the data, and the problem is, I think that we don't... Let me just look this up real quick. Alright, so I think the issue here is that both of these are actually valid heaps. They're just different, so you get a different one when you do heap pop and when you pop and then do heapify, but both are valid heaps. The only thing you need to understand is that when you do heap pop, you get a valid heap and you don't get the same thing that you get when doing pop, because pop just takes the first element and leaves everything the way it is. And heap pop actually cares about maintaining the heap invariant, so actually having a valid heap. So this property that each node is having only childs that are larger or greater. So let's delete that again, and we're going to talk about the next function here, which is heap push, adding a value to the heap. And for that, we're going to print the data after the heap pop, and then we're going to just say heap q.heap push, and we're going to use data here, and we're going to enter a new value. Let's go with something that will not just end up in the end. Let's go with a 2. Print data, because the problem is when you add something like, I think, 19, for example, it should end up in just as a last value. In this case, you can see that when you just append, if you would just append this value, it would just end up in the end. In this case, it did not end up in the end. It's somewhere here, one of these 2s. Whereas if I go with 19, for example, I think 19 is a value that should work. It will just remain in the end. Why? Because this still satisfies the heap property. So this is still a heap, a valid heap. You don't need to move the 19. You can just append it and it still works. Whereas with other values, that's not the case. So we can play around a little bit, maybe with a 4. We get something else. No, a 4 is still fine, I think, because let's think about this. We have 1, we have 2, 17, we have 2, 3, we have 65, 43, and then we have 44 and 10, and then we have 20 and 4, which is fine. So you have to take something in this case which is less than 3, otherwise it will just remain in the end. But the important thing is that heap push essentially pushes a new value and then gets it into a position where it belongs. So I think if we do it one more time, if I go ahead and say 19 and maybe 21 here, those should not be in the end. Okay, 21 is in the end, but 19 was placed in a different place because the 3 was already having 2 childs, so we now had more room, more flexibility there. So this is the heap push function. Now, one thing that you may be asking right now is, this is all a min heap. How do I turn this into a max heap? And for that, there is a kind of hacky way, and there is a way that is undocumented. So both of them are not necessarily the best ways. Probably you should implement your own data structure if you want to have a max heap, because heap_q offers a min heap. However, what you can do, this is probably the easy way, you can just invert the numbers. So everything that is a 10 becomes a -10. Everything that's a 20 becomes a -20, and so on and so forth. So you don't have to use these values. You can just negate them, because then 1 becomes -1 and 65 becomes -65. So now it's less than -1. So everything is inverted. This is one way to turn this into a min heap. Or a max heap actually. So I can say data equals -x for x in data. And there you go. Now everything is reversed if you want that. However, you can also use some undocumented functions of heap_q. So you can go ahead and say heap_q dot and then underscore heapify underscore max data. And then you're going to see that this is now a max heap. However, you can see that PyCharm doesn't even recognize the function. It says cannot find. It's undocumented, and probably not something you should use. If you want to use a max heap, use your own implementation. And for the heap pop, you have the same thing. So we can say heap_q dot underscore heap pop underscore max data, and then just print the result here. And this is still going to work. However, of course, yeah, this is undocumented. So best way.
Heap push, heap pop. Turn a list with the n largest elements from the dataset defined by iterable. Okay, don't need this. We can do, okay, the what does documentation say? Heap queue dot n largest. N, our n would be our PQ. Alright, return a list of n, invert key, the iterable, and the key. Iterable. Be like every 2 values or something. Oh, n largest. Okay, so the iterable is the data set. Right? Oh, yeah, ran 5.4. Okay. Now what do we want to do? We want to return, okay, the largest 0. -1. Just 1 -1. I believe that should work. Okay. Okay, what is this time complexity? What is this time complexity? Constant time. Oh. And log in. Okay, so what would be the other way than just the linear way to do this? I believe take so max 1 is equal to 0, max 2 is equal to 0. We go for I and nums. We check, okay. Okay, if I Ryan times we would go, okay, if I is greater than max 1, then max 1 is equal to I. I know we would do, okay, max 2 is equal to max 1. 1 is equal to I. Let's return max 1, return max 2. Oh shit, I want print. Max 2. Okay, we got 5 and 4. So then we would just return. Okay, well. Max1. 1 times max2 minus 1. One, 5, 4, 5. Oh. How did we get a -9 output, dude? What the? How do we get 0? Oh. When our first value is the highest, it's never going to be higher again. I think we need an else if. Else if I is greater than or equal to max2, we make max2 equal to I. There we go. Okay. Sweet. We have both versions. Nice. Okay, so we learned about a heap queue. We learned about a tree. Let's learn about, okay. Let's learn about a try, they call it. Let's do difficulty easy. We sort by acceptance. Count prefix suffix pairs 1. Okay. Rolling hash, dude. What the hell is a rolling hash? The rolling hash data structures. That rolls through a lot. A rolling hash. Interesting. Okay. Alright, this will be our last problem of the day. And then we're going to jump into doing some other things. You're given a 0 index string array words. Let's define a Boolean function is prefix. That takes 2 strings, string 1 and string 2. Turns true if string 1 is both a prefix and a suffix of string 2 and false otherwise. For example, is prefix and suffix abba. Abba is true because abba is a prefix of ab, aba. Also. Okay. Reserve for to count prefix and suffix pairs 1. Tree data structure. I think there's other ways that you can do this. Prefix and a suffix. Find a tree-based solution. Tree-based solution be used with nodes? That's what I'm confused about. Like, okay. So we create multiple different tree. My wrist is itchy, bro. So we do. It's probably a little bit overkill for this problem, but they instead here they do a hash map. Author. How can we do this without a tree? Just because I got stuff to do, I'm going to solve this without a tree. And we'll come back to it tomorrow. And we'll solve it with a tree. Because a tree solution is like just crazy overkill. Why would anyone like code that much like to solve something like this? I don't understand. Like, I'm just trying to figure out the problem. Like, I don't really understand. Okay, I think I understand. Okay. So, for word in words. I think we can use a set here. Let's create a hash here to compare. Oh my gosh. We need to loop through. One in range 1 to so we got A ABBA, A ABBA ABBA, A. Then we got ABBA. Right, we need to go from, let's do I, J. We'll go from I plus 1. Length words. Oh, this needs to be J. I can concatenate string. What's wrong here? I in range length words. Alright, we want to just put this in. Oh, this needs to be words. I. Okay, so we got A, ABBA, A, ABBA, A. And we got ABBA, ABBA, A. Then ABBA, A. Okay. So then we want to create probably some helper function. F is prefix and suffix. We pass in our let's do prefix word. Okay. Let me search this up in Python. Are you using a set? I think you can. if prefix I guess can we pass in, okay, is prefix and suffix, pass in the set of the word I. Okay, the set of the word I, and then set of word J. Can we easily just compare this using an if statement? I probably don't think so, but if is prefix and suffix, if prefix in word, maybe the prefix can just be word I. Prefix in word, we return true, else return false. Okay. Well, if is prefix word I equal to true, then we count by 1. Count plus equal to 1. Count is equal to 0. I believe we can just return then. Return the count. Oh, return the count. I don't think this is gonna work. I just don't know the trick around it. You're checking if prefix in word, we should check substring, not whether it's a prefix and suffix. Really, this starts with and ends with methods, dude? No way, bro. Are you serious? Starts with method Python. Oh my god. There's an ends with method. No way, bro. Dude. Okay, how would you do it? Okay, if prefix dot starts word dot starts with prefix and word dot ends with prefix, then we return true, right? Don't believe we need this hashy anymore. Let's get rid of this set. I believe we need to wrap it in a set at all. Word is not defined. Words. Okay, there we go. How will we do it without the starts with and ends with method? No, fuck. I don't want to use that. Okay, mine's slow as hell. This guy uses a tree. It's probably because I have a hashy here. Okay, if we didn't have the starts with method, let's check. Okay, well, we'd have to check, well, if n is equal to the length of prefix, right? So obviously, if n is greater than word, we would return false because that's incorrect. Okay. Okay, this checks prefix, right? For I in range n, if prefix I does not equal word I, right? Then we would just return false, right? Now we check the suffix. Check suffix. Oh! How do you spell suffix, man? 2s. Is prefix 2s? No, it's not, right? Okay. Check suffix. Check prefix, check suffix, right? We would do the same thing. Right, but we would loop for I in range n. We would check, okay, if prefix I guess we could loop from reverse, right? So we could go, well, from how we loop from reverse? We would go from length. We will go from n minus 1 minus 1 minus 1. For loop range Python. Start, stop, step. So we start at the range length minus 1. We stop at, I think we need to really say the stop, but we would just go, we just go minus 1. And we check, well, if prefix I does not equal word I, and we just return false. Otherwise, we return true, right? I know this is wrong. I'm going to run it, but I'm pretty confident that that loop is wrong. Yeah. If n is greater than the length of the word. Oh shit, that worked. No way, that worked, bro. I think the suffix is incorrect. I believe this suffix missing step and wrong indices. Same indices as prefix check, wrong. Fine. We don't have to step like that. Just go from range n. If word n minus length word, right, minus n plus I. So we're going to the length of the word, right, minus n, which is the length of the prefix, plus I. I don't get the plus I there. What does a plus I do? Y plus I, you're comparing the whole prefix against the last n characters of the word, so like that, and it gives a starting index of the suffix in the word plus I walks through each character of that suffix alongside prefix I. Okay. I understand. Okay. Okay, I'm gonna call a video. We're gonna do the tree solution for that tomorrow. It's a little bit longer of a solution, but yeah, I appreciate you guys watching, and I will see you tomorrow.